Usually when we talk about using a computer, there is this baseline expectation of, well, frictionless interaction.
Right. A highly curated experience.
Exactly. You click an icon and an application opens, you type on a keyboard, and words just render on the screen. It is designed so you never really have to think about the metal and the silicon that's actually doing all the heavy lifting.
I mean, it's very much like driving a car. You turn the steering wheel, you press the gas pedal, and the vehicle moves forward.
Yeah, you don't need to understand, like, the precise fuel injection timing to get to the grocery store.
Or the gear ratios in the transmission.
Right. But today, for you, the listener, we are pulling that car into the garage, we're popping the hood, and we are handing you the mechanic's overalls.
We are definitely bypassing that curated experience today.
We really are. We are grabbing the keys to the kingdom to look at the hidden control panels, the administrative frameworks, and the underlying architecture of the Microsoft Windows operating system. Today's deep dive is all about decoding the source material from CompTIA A so you can transition from a casual user into a true system manager.
Yeah, because we are stripping away those abstraction layers. When you spend all your time in that safe, curated user space, well, you are entirely at the mercy of the machine when things go wrong.
Oh, totally. If an app hangs, you're just stuck.
Exactly. Or if a piece of hardware stops responding, the casual user just reboots and hopes for the best. But stepping behind the curtain to understand the administrative architecture, that fundamentally shifts your relationship with the machine.
You transition from being a passenger to an active system manager. You start dictating terms to the OS.
Right. You take control.
Okay, let's unpack this. If we are going to start tearing down the engine, we need a toolbox. You cannot walk onto a construction site with bare hands and expect to frame a house.
No, you definitely need your tools organized.
And in the Windows environment, that master toolbox is the Microsoft Management Console, the MMC.
The good old MMC.
Yeah, you can literally pull this up by typing MMC into a run prompt. But, the first time I did that years ago, I was incredibly underwhelmed.
Because it's completely empty.
Yes. It opens up, and it is essentially just a blank gray window. There's nothing in it. It feels completely useless, at least until you understand what it actually is.
Well, the blank slate is the entire point, actually.
Yeah.
The MMC is not a management tool in itself. It's a component object model framework that's designed to host the management tools.
It's just a container.
Exactly. Before this architecture was introduced, system administration was just an absolute nightmare of fragmented utilities.
Oh, I can imagine.
Yeah, you had one program written in one language to manage users, then a completely different standalone application to manage your disks, and another one entirely for network protocol.
Just a mess of different windows.
Yeah, right. So Microsoft unified the interface, they created the standard container, and then built all the actual tools as snap-ins that plug directly into it.
I always think of it like a customizable tactical utility belt. You do not carry every single gadget you own at all times. That would be chaotic and heavy.
We'd be weighed down.
So you look at the job in front of you, and you snap on only the pouches you need for that day. If you were doing network reconnaissance, you snap in the event viewer and maybe the IP security monitor.
Right, and if you are provisioning hardware, you snap in disk management and device manager. It's tailored.
Exactly.
And that modularity offers a massive advantage in enterprise environments, specifically regarding access control. You can load a blank MMC, add only the specific snap-ins required for a job, and save that exact configuration as a .msc file.
And the MSC file, right? Which just remembers the layout.
Yeah, it's an XML-based file.
Yeah.
So imagine you have a junior help desk technician. Their sole responsibility is managing employee passwords and unlocking accounts.
You definitely do not want them having access to the tool that reformats the company's server drives.
Precisely the opposite. You want their environment restricted. So a senior architect builds a custom MMC, snaps in only the Active Directory users and computers module, saves it, and deploys it to the junior technician.
Oh, wow. So when they open it, it's completely streamlined.
Right. It's a distraction-free interface tailored perfectly to their clearance level. They never even see the options to break the wider system.
Controlled power. I really love that.
Yeah.
So let's look at one of the most critical snap-ins that lives inside this framework, the device manager.
A classic.
You get to it by launching devmgmt.msc or just hitting the Windows key plus X. This is the translation layer. It's where the OS shows you every physical piece of hardware it currently detects on the motherboard. Keyboards, biometric scanners, network cards, you name it.
It is the visual representation of the hardware abstraction layer. When the system boots, the plug-and-play manager queries every bus, right? Like the PCIe slots, the USB controllers.
Just checking what's out there.
Exactly. It demands identification from whatever is plugged in.
Yeah.
And Device Manager enumerates that inventory.
And it uses a very distinct visual language, doesn't
Yeah.
it? Usually everything just looks like a neat list. And conceptually, we think of that as a green check mark. Healthy hardware.
Right. Everything is communicating.
But then we have the problem states.
Mm-hmm.
A gray down arrow indicates the device is disabled. The hardware is physically present, drawing power, but the OS is explicitly ignoring it.
Right.
And then there's the one that gives every IT professional mild anxiety, the yellow warning triangle with the exclamation point.
Oh, yeah, the dreaded yellow bang. That indicates a fundamental breakdown in communication. The plug-and-play manager found a device, pulled its hardware ID, but it cannot successfly initialize it.
You usually see this under a generic category like other devices, right?
Yeah, maybe next to something really cryptic like 802.111 NICSCS. The operating system knows it is a piece of silicon, it knows where it's plugged in, but it lacks the instruction manual to tell it what to do.
And that instruction manual is the driver.
Yes. The driver operates in the kernel space. It is highly privileged code that translates the generic commands of the OS into the highly specific electrical signals required by that exact model of network card.
So if the yellow triangle is there, the driver is either missing or corrupted or maybe causing a memory conflict.
Exactly.
So dealing with that yellow triangle brings up the right-click context menu actions. Say you right-click that misbehaving NAC, your first instinct is probably to update the driver, right?
Yeah.
Reaching out to Windows Update or a manufacturer file.
That's the usual first step, yeah.
But let's say the driver is there, it's theoretically up to date, but this specific device, let's say a high-end webcam, is actively causing the system to blue screen and crash. I want to push back on this standard troubleshooting flow here.
Okay, let's hear it.
The options are disable device or uninstall device. If this webcam is nuking my system, my immediate reaction is to click uninstall. Nuke it from orbit, start fresh. Why is disable considered the better first step?
What's fascinating here is how the OS sandboxes malfunctioning hardware. Uninstalling a device that is actively plugged in is a massive trap.
A trap.
Yeah, a trap born from Windows wanting to be endlessly helpful. If your system is crashing due to a kernel panic from that webcam, you are dealing with a severe variable. You have to isolate it.
Okay, that makes sense.
If you click disable, the operating system immediately stops loading that specific driver into memory and it revokes its resources. The device just goes dormant, you reboot. If the crashes stop, you have definitively isolated the problem.
But wait, couldn't I do that just by uninstalling it?
Well, if you click uninstall, you are telling Windows to delete the configuration, but the physical webcam is still plugged into the USB port.
Right.
So the moment you reboot, the plug-and-play manager wakes up, scans the USB bus, and says, "Oh, look, a new webcam. Let me be incredibly helpful," and immediately reinstall the exact same corrupted driver I have cached locally.
Oh, wow. So before you even reach the desktop, the bad driver is reloaded and the system crashes again.
Exactly. You've learned absolutely nothing.
It's the digital equivalent of a boomerang. You throw the problem away, and Windows proudly catches it and hands it right back to you. So disable acts as a quarantine.
It preserves the forensic state without losing the driver configuration permanently. Once you confirm it's the root cause, then you take action. Maybe you update it while disabled. Or you use the remove hardware sequence.
Meaning you uninstall the software brain and then physically unplug the USB cable before it can reboot and reinstall.
Precisely. You sever the connection.
Okay, so we've used the MMC and Device Manager to get the hardware whispering smoothly to the motherboard. It's quarantined, updated, humming, but that raw metal is useless until we impose order on it. We have to map out where the data actually lives.
We are transitioning from the physical hardware to the architecture of storage itself.
Right, into the disk management snap-in, or disk mgmt.msc. This is where we define the logical boundaries. Say you buy a brand new high-capacity hard drive, you mount it in the case, plug in the SATA data and power cables, you boot into Windows, open File Explorer, and, well, nothing.
Yeah, the drive is a ghost to the user.
It doesn't exist as a letter, but if you open disk management, you see it sitting there with a stark black bar across the top, labeled unallocated and not initialized.
Because at that moment, the drive is just a vast, empty expanse of raw block storage. Windows sees the physical platter, but there is no index, no table of contents. It's land without borders.
So before you can write a single text file to it, you must initialize it.
You are forcing the OS to write a master ledger at the very beginning of the disk that dictates how the rest of the space will be organized.
And when you right-click to do that, Windows forces a permanent architectural choice. It presents a fork in the road, MBR or GPT.
The Great Divide.
Exactly. Let's break down why this matters so much, starting with the legacy heavyweight, MBR, the master boot record. This was the undisputed standard for decades, right? Supporting older systems like Windows XP.
Yeah, and Windows 7 32-bit. But it has extreme limitations. It only allows for 4 primary partitions, and its absolute maximum capacity is 2 terabytes.
I really want to dig into that capacity limit. Why 2 terabytes? It feels like such an arbitrary number today. Did engineers back then just pick a number they thought we'd never reach?
It's not arbitrary at all. It is entirely rooted in the mathematics of how computers count. MBR uses logical block addressing, or LBA, to find data.
Think of LBA as assigning a sequential number to every single sector on the drive.
Right, Sector 1, Sector 2, all the way up. MBR was designed using a 32-bit architecture for those addresses.
So the maximum number of addresses is limited by 32 bits of binary code.
Exactly. 2 to the power of 32 yields roughly 4.29 billion possible addresses.
Okay, tracking with you so far.
And the standard size of a physical sector on a hard drive for decades was 512 bytes. So if you take your 4.29 billion addresses and multiply them by 512 bytes, you hit a mathematical ceiling at exactly 2.19 terabytes.
Wow. So the ledger simply runs out of numbers to assign to anything beyond that physical point. The rest of the drive becomes invisible dark matter.
It's a hard mathematical wall, which completely explains why the industry had to abandon it and create GPT, the GID partition table.
GPT requires modern UEFI firmware, right, instead of the old legacy BIOS.
Yes, and it bumps that partition limit from 4 up to 128 primary partitions.
But the capacity jump is what is truly mind-bending. Because it uses 64-bit logical block addressing, the limit is no longer 2 terabytes. Here's where it gets really interesting. The new limit is 9.4 zettabytes.
The scale of a zettabyte is difficult for the human brain to process. 1 zettabyte is 1 billion terabytes.
It's absurd. If 1 terabyte was a mile of road, the 2 terabyte MBR limit gets you to the grocery store and back. The 9.4 zettabyte GPT limit allows you to build a road from Earth to the edge of the observable universe.
And then pave it a few more times.
Exactly. It is functionally infinite. So, knowing that GPT is superior in every single metric, I have to push back. If GPT is so vastly superior, why do we even bother learning about MBR anymore? Why isn't it completely dead?
Because enterprise IT is rarely a pristine modern environment. You inherit legacy infrastructure. Imagine you are hired to maintain the network for a massive industrial plant.
Okay, I'm picturing it.
There is a multi-million-dollar robotic assembly line, and the only computer capable of interfacing with it is a specialized machine running a custom 32-bit version of Windows XP.
And that relies on legacy BIOS.
Which means it must boot from an MBR initialized disk. If that hard drive fails and you pull a drive off the shelf and initialize it as GPT, the motherboard will not know how to read the ledger. The robotic line halts. Millions of dollars are lost because an admin didn't understand legacy boot constraints.
The tech debt of the real world dictates our skill sets. That makes total sense. Okay, sticking with MBR for just a second, let's explore that 4 partition limit. Those are primary partitions, which are crucial because they can be marked as active and actually boot an OS.
Right.
But what if I have an MBR drive and I want to chop it up into 6 different drive letters, C for OS, D for data, E for media, and so on? Am I just out of luck?
No, this is where we encounter the extended partition, which is a very clever workaround. You can't have 6 primary partitions, but you can create 3 primary partitions and then use your 4th slot to create 1 extended partition.
I envision the extended partition not as a room, but as an empty shipping container placed on the property.
That's a perfect visualization. The extended partition itself cannot hold data, and it absolutely cannot boot an OS. But inside that container, you can create an endless number of logical partitions.
So you carve out 10 logical partitions inside that space, and Windows assigns a drive letter to each one.
Yes, it bypasses the master ledger limitation by nesting a subledger inside that 4th slot.
Now, obviously, with GPT allowing 128 primary partitions, that dance is mostly a thing of the past. But whether we use MBR or GPT, disk management also lets us deal with storage arrays. In the past, you needed expensive hardware RAID controllers. Today, Windows offers storage spaces.
Storage spaces is a massive shift towards software-defined storage. It abstracts the physical drives entirely.
You can mix and match, right?
Oh, absolutely. You can take a 1 terabyte SATA drive, a 2 terabyte USB external, and a 500 gigabyte SSD and pool them all into one massive virtual drive. Windows handles the complex RAID algorithms in the background.
So if you set up a parity layout and a drive physically catches fire, the OS uses the parity math on the surviving drives to rebuild the data.
Real-time rebuilds. Yes, the user never loses access.
It democratizes enterprise-grade protection. But let's look at a simpler scenario. You aren't building a parity array. You just have a single C drive, and it's flashing red because it's 99% full. But you notice a block of black unallocated space right next to it in disk management. You don't need to format the drive to use it, do you?
Not at all. You use the Extend Volume Wizard. As long as the unallocated space is physically contiguous, meaning right next to the partition on the same physical disk, you just right-click and extend. The file system dynamically absorbs the raw space without dropping data or needing a reboot.
So we've built our digital house, and we've expanded the rooms. But once data is living on these partitions, we have to maintain the structural integrity. The foundational tool for this is CheckDisk.
CheckDisk. CheckDisk is incredibly deep. It analyzes the NTFS master file table, the database that tracks which sector holds which piece of data.
Making sure the metadata matches physical reality.
Exactly. If there is an orphan file record, it resolves the conflict to prevent data corruption.
Now, a good rule of thumb for drive health is the 20% rule, right? Always keep at least 20% of your system drive completely free. People ignore this constantly, filling a drive until there are 5 megabytes left, and then they wonder why it takes 10 minutes to open a browser. Why does a lack of storage destroy processing speed?
Because the OS treats empty space as critical infrastructure. It's a staging area. Windows uses virtual memory, a massive file called pagefile.sys, to shuffle data in and out of RAM. If the drive is full, the page file cannot expand dynamically.
Plus, modern file systems like NTFS require contiguous free space to write new data efficiently.
Right, if you only have slivers of free space, the OS chops every new file into hundreds of microscopic fragments just to squeeze them in, driving the processing overhead through the roof.
Which perfectly transitions us to optimization, because the rules change dramatically depending on the physical nature of the drive. Let's look at the classic mechanical hard disk drive, the HDD. The optimization here is defragmentation.
You have to visualize the mechanical reality of an HDD. It has physical glass or aluminum platters coated in magnetic material, spinning at 7,200 RPM. Hovering nanometers above those platters is a read-write head on an actuator arm, just like a record player noodle.
So when Windows saves a huge video file on a crowded drive, it fragments it.
Yeah.
Piece A near the edge, piece B near the center.
And when the user watches it later, that physical head is violently darting back and forth across the spinning platter to collect the pieces. That delay is called seek time. And waiting for the right part to spin under the head is rotational latency.
Defragmentation takes all those scattered pieces, reads them, and rewrites them in perfectly sequential order. So performance skyrockets.
Exactly. One smooth sweep of the rehead.
Okay, so if defragmentation is so magical, I should absolutely run it on my brand new, ultra-fast solid-state drive, right?
Doing so would be one of the worst administrative mistakes you could make.
Wait, really?
You should never defragment an SSD. It has 0 moving parts. It's just NAND flash memory chips, no physical read head, no spinning platter. The electrical controller can access a memory cell at the edge of the drive in the exact same fraction of a millisecond as the center.
The concept of physical location is irrelevant to an electron.
Precisely. A heavily fragmented file opens just as instantly as a perfectly sequential file on an SSD. But worse than being useless, defragmentation is actively destructive to flash memory.
How so?
Flash memory has a finite lifespan measured in program array cycles. Every time you write voltage, you degrade the silicon a tiny bit. Defragmentation is just reading and rewriting gigabytes of data. You are deliberately burning through its finite lifespan for no benefit.
So how do we actually maintain an SSD?
We use a command called trim. See, on a mechanical drive, you overwrite data instantly by flipping magnetic polarity. But flash memory cannot do that. A cell must be explicitly erased before new data can be written.
And erasing takes extra time.
A massive amount of time in computing terms. When you delete a file, Windows just marks the space as available. If an SSD doesn't know it's deleted and tries to save there later, it has to pause, erase the block, and then write. That lag is write amplification.
So Trim solves this by having Windows whisper to the SSD controller in the background, "Hey, the user deleted these files. Go do the heavy erasing now while we're idle."
Exactly. It ensures the cells are clean and ready to accept voltage instantly when needed.
It's brilliant how the software maintenance has to change based on the physical reality of the hardware. But managing all of this manually, running Trim, clearing caches, running disk checks, that would turn you into a full-time janitor for your
Yeah,
computer.
nobody has time for that.
Right. We need to transition to automation, which brings us to the task scheduler.
This is where we separate the reactive user from the proactive system administrator.
A proactive admin builds an environment that maintains itself. And Task Scheduler is the digital butler for this. It relies on triggers and actions. Triggers are the when, actions are the what. A lot of people just think of it as an alarm clock, like running a scan every Friday. But it's far more deeply integrated.
Oh, definitely. Event-based triggers are incredibly powerful. Windows logs everything in the event viewer. Every login, every driver failure, it generates a unique event ID. You can tell Task Scheduler, listen for event ID 4624, a successful logon, and trigger the action the millisecond that happens.
And actions can be chained together for complex workflows, like managing a database server. Trigger at 3 a.m. Action 1, run a script to pause the database. Action 2, back up the files. Action 3, query the result and email the IT team. Then restart the service.
And all this happens while the admin is asleep. Plus, you don't even need a user logged in. You can run tasks as the local system account, giving it highest privileges to modify files invisibly.
Which brings up a critical architectural pivot. We have organized storage, automated maintenance, the machine is humming. But a well-maintained machine is a target. Who gets to use it, and what are they allowed to touch? We're moving to users, groups, and group policy.
We are defining the blast radius. Every user is a potential vector for failure, malicious, or just ignorant.
Let's start locally, using lusrmgr.msc. You mint new identities here, but the username is just a name tag, right? It has no inherent power. The actual power comes from security groups.
Yes, the OS doesn't care about your username. It generates a security identifier, a SID, a massive unique string. That SID goes into a group, and the group gets the permissions.
I visualize it like corporate physical security. You get an RFID badge when hired, which is your account, but what doors it unlocks depends on your assigned group. Let's look at the administrators group, the master key.
If your SID is in administrators, you have an unrestricted access token. You can format drives, alter core registry keys, basically destroy the OS. In a managed environment, almost no one should log in as an admin for daily tasks.
Because if an admin opens a malicious email attachment, the malware inherits that master key. It embeds into the core system instantly. That's why most people are in the standard users group.
It's a brilliantly designed containment zone. You get a restricted access token, you can browse the web, use your own documents folder, but you are walled off from the system architecture.
If a standard user tries to install unapproved software, the screen dims and demands an admin password.
Yeah.
That's user account control, right? UAC.
Exactly. And the screen dimming is the secure desktop. It isolates the prompt to prevent malicious scripts from auto-clicking.
Yeah.
Yes, it physically stops the action. If they download ransomware, it can encrypt their personal files, but it can't touch the Windows System 32 folder or other users. The blast radius is contained.
And finally, the guest group. If users have the key to their office, guests are like someone sitting in the lobby under constant surveillance.
Guests are conceptually fascinating. Historically, they could browse, and upon logout, the OS aggressively wiped every temporary file and setting they touched. But any open door is a vulnerability, so modern environments usually leave it disabled by default.
So local groups are great for a single laptop. But what if you're the admin for a university with 5,000 computers? You can't walk to every machine to configure passwords. That does not scale.
Which is why enterprise relies on group policy. It's the overarching rulebook, usually pushed out via Active Directory.
The granularity in group policy is staggering. Enforcing complex passwords, managing updates. One fascinating example from the source material is disabling USB storage. To a user, it feels draconian just wanting to transfer a PDF. This raises an important question. Why would IT deploy a policy to prevent a basic hardware function?
Because a USB port in a corporate setting is a massive security hole. It bypasses firewalls and email scanners entirely. It's a vector for data exfiltration and malware insertion.
Pulling secrets out and pushing poison in.
Precisely. A disgruntled employee could quietly copy gigabytes of proprietary code to a micro USB and walk out. The network appliances would never know. Conversely, an attacker could drop infected USB drives in the parking lot.
Human curiosity takes over, someone plugs it in to see what's on it.
And an auto-run script executes ransomware. Group policy solves this architecturally. By setting removable disks to deny read access and deny write access, the policy overrides the driver stack. It doesn't matter if the CEO plugs it in, the drive refuses to mount. The attack vector is sealed at the OS level universally.
That is the true power. But it's vital to remember, group policy is just a graphical mask. When you toggle a setting, you're actually rewriting the raw code deep in the OS.
Yeah, it's a user-friendly interface for manipulating the registry. Disabling USBs just changes the start value in the USB registry key from a 3 to a 4.
Which brings us to the raw architecture itself. If we strip away the menus, we interact with the system's DNA directly, the registry and the certificate manager. Let's start with the registry editor, regedit.msc. It's the central database for all OS, hardware, and app settings. I call it the DNA of Windows.
It's the absolute core. Before it existed, older OSs used hundreds of unorganized .ini text files. The registry centralized everything into a structured binary format.
It looks like a file folder system, but the root folders are hives. Let's dissect the 5 main ones. First, HKey classes root or HKCR. This handles file associations. In plain English, how does this work?
Imagine you double-click a report.pdf. How does the OS know to launch Acrobat instead of Word? When you click, Windows Queries HKCR finds the .pdf extension key and reads the path to the Acrobat executable. If HKCR is corrupted, the computer has absolutely no idea what app to use for a text file.
It provides context. Next is HKey currentisor, HKCU.
This is your personalized reality. Desktop wallpaper, mouse speed. When you log in, Windows reads a hidden NTSARA DAT file and loads it into HKCU in RAM, building your custom environment on the fly.
Then the heavy hitter, HKey local machine, HKLM.
The machine's identity, independent of users. It holds the boot configuration, driver order, and core software rules. Group policies are usually written here.
Fourth is HK users, HKU.
The master container for all user profiles. HKCU is actually just a shortcut pointing to your specific subfolder in HKU while you're logged in.
And finally, HKey current config, HKCC, for the hardware profile in use.
Vital for modular hardware. If you move a laptop from battery power to a docking station with 3 monitors, HKCC instantly updates to tell the kernel to load new drivers.
Inside these folders are values like string values and dwords, which act as binary switches. You can modify them to fix deep issues, but there's a severe warning here.
Editing the registry is open heart surgery without anesthesia. There is no undo button. If you change a 1 to a 0 in HKLM and accidentally disable the hard drive controller, the computer will instantly crash.
And when you reboot, you just get a black screen because the system can't even start its kernel.
Exactly.
Which is why you always export a backup before editing. Now, the registry handles internal logic, but computers have to talk to the chaotic internet. How does this code know who to trust? That brings us to Certificate Manager.
We're moving into public key infrastructure. Certificates establish trust in a zero-trust environment.
They're called digital passports. But let's look at the math. The internet is insecure. If I check my bank balance, the data bounces through random routers. Anything can intercept it, right? A man-in-the-middle attack.
Right, so we encrypt it, but how do you agree on a password when the channel is compromised?
This is asymmetric cryptography. 2 keys, public and private. The bank hands my computer a certificate with their public key. My computer uses it to lock my password in a mathematical box. The brilliant part is the public key can only lock the box. It cannot unlock it.
Only the bank's private key can unlock it.
So even if a router admin intercepts it, it's useless to them. But this relies on knowing the certificate actually came from the bank.
Exactly. How do you verify the identity of the person handing you the key?
This is where certmgr.msc comes in. It organizes certificates into stores. Most importantly, the trusted root certification authorities.
Root authorities like DigiCert are arbiters of trust. They verify a company's identity, then use their own secure private key to digitally sign the company's certificate.
And Microsoft preloads these root authority public keys when you install Windows.
So when the bank hands you a certificate, your computer checks the signature against the trusted root store. If the math checks out, trust is established and you get the secure padlock icon.
But if a hacker breaches an authority and steals a valid certificate, they could sign malware with it.
A nightmare scenario. The OS would see the signature, trace it to the root store, say, this is trusted, and execute the malware with high privileges. If we connect this to the bigger picture, this is why managing certificate stores is so critical.
If a certificate is compromised, You must update revocation lists and manually untrust it. It's like flagging a stolen passport at customs. Now, we have spent this whole time using graphical tools. But true mastery sometimes requires stripping away the GUI and using native text. The command line tools.
We are dropping into the terminal. It's intimidating, but it's the most direct way to communicate with the kernel.
And it's self-documenting. If you type a command followed by innate, like chi-teski, it prints the manual instantly.
Let's explore why you'd choose text over GUI for copying data. In the GUI, you copy and paste. But what if you're copying a 5 terabyte directory over a spotty network?
File Explorer will analyze it for 10 minutes, start, and if the network drops for a microsecond, it completely fails. You have to start over.
The GUI is fragile. The command line offers Xcopy. You can use E to copy every subdirectory and I to force directory creation. But for true resilience, admins use Robocopy.
Robocopy is a beast.
If the network drops, it doesn't fail. It waits and resumes from the exact byte where it left off. You can use MT for multi-threading, copying 64 files simultaneously, and copy all to perfectly mirror access control lists. The GUI can't do that.
What about disk management? The CLI equivalent is diskpart. You use text commands to select and mount volumes. So what does this all mean? Why memorize unforgiving text strings when the disk management GUI is foolproof?
Because the GUI is a luxury. It requires a massive stack of dependencies. What happens when the system is catastrophically corrupted and won't boot past a boot loop?
The GUI is gone.
You fall back to the Windows recovery environment, Winry. You're staring at a black terminal screen. If you don't know how to use diskpart to find the volume and Robocopy to extract the data to a USB drive, that data is lost forever. It's a vital survival mechanism.
And many enterprise servers run headless anyway, completely without a GUI.
The final command here is triggerdisk in the CLI. In a recovery state, it unlocks physical triage.
Triggerdisk fixes logical errors. But if an HDD was dropped or an SSD cell burned out, you have a physical bad sector.
That's where you deploy the R switch. It tests the physical integrity of every sector.
And if it hits a bad sector with a critical boot file?
It attempts physical recovery. It strains to read the magnetic signals, moves the data to a reserve sector, updates the index, and marks the damaged sector as toxic so it's never used again. Surgical triage purely through text.
We have covered massive architectural ground today. From the MMC toolbox and device manager quarantine to storage math with MBR and GPT, and adapting maintenance for HDDs versus SSDs.
We moved into proactive automation with Task Scheduler, established security with users, groups, and group policy.
And finally descended into core, manipulating the registry DNA, securing certificate manager trust, and wielding the native power of the command line.
You stop reacting to the interface and start commanding the infrastructure.
And that leads to a final thought for you, the listener. These tools grant you incredible, almost godlike control. You define reality for the hardware. But with that power comes immense risk. As with the registry, typing one wrong keystroke can silently destroy the system you are trying to optimize. Where is the line between optimizing your technology to absolute perfection and over-tinkering to the point of catastrophic collapse?
The more power and access you demand, the smaller your margin for error becomes.
Thank you for joining us on this deep dive. Next time you boot up, we hope you don't just see the polished desktop, but look at your machine with a new sense of architectural mastery and respect for the raw power humming just beneath the surface.